Hello everyone, today I'm going to share with you one of my new favorite functions, Einsum. The basic idea of Einsum is that there's a lot of matrix operations like the ones shown here that can be written using index notation. Furthermore, anytime you have these index expressions, a lot of this notation is actually redundant, so you can implicitly capture the entire operation if you only include the indices like so. Not only is this a convenient alternative to all the matrix terminology like numpy.sum, numpy.mapmul, and numpy.transpose, but it can change the way you think about matrix operations. So a quick disclaimer before we dive into some examples, I'm not a physicist, I'm a programmer, so as a result we're going to be focusing on the conventions used by libraries like Numpy, Pytorch, and Tensorflow. And specifically I'll show code examples in Python which has index notation that starts from 0. But if you feel more comfortable using index notation starting from 1, that's totally fine as long as you stay consistent. First, we'll start with a quintessential example of matrix multiplication, matrix A times B equals C. As you know, this operation consists of lining up the rows of A with the columns of B, and the corresponding element of C will be the dot product between that row and column. The question for us is, how do we convert this to summation notation, which will in turn let us write the Einstein notation? The mathematically inclined will probably know that the way to write an expression in summation notation is to write an equation that defines the ijth element of your output matrix C. This implicitly tells us that we'll have to loop through all indices I and j in order to get the full C matrix. From there, we know that the ijth element of C will require that you get the ith row of A and the jth column of B. And then our index k is the shared index that's going to do the elementwise multiplication and sum. So now, once you have that, you just take the indices and voila, there you go, you have your Einsum expression. The important thing to note is that indices are used to iterate over a particular dimension, but you can also think of the index as a label for that dimension. When you assign this label, you're specifying that the dimension has a certain size, and any other dimensions with the same label will also have the same size. With all that being said, here are some rules that can help you shortcut the thinking process without always having to write out the whole summation notation. Firstly, an Einsum string is composed first of the input matrices and their corresponding index labels, followed by the output labels and their corresponding index labels, and then separated by this arrow operator, which is basically just a make the dimensions work operator. So the arrow is kind of the most confusing part. We'll get to that. So when constructing this string, the first thing that you should have in mind is that if an index label is in the output, then that dimension is kept. So these are shown in blue. And then second, if an index label is not in the output, then that dimension is going to be removed. But you can use a variety of different operations. So this could be summation, this could be matrix multiplication, this could be elementwise multiplication, selecting diagonal elements, etc. So this is kind of the challenge of Einsum, is that there's all of these different things that you could do, but it's all kind of implicit in the way that the subscripts are written. If you think about the different options, there's only really one that ever makes sense. So this is what takes practice, but this is what makes it powerful. The last two rules are, if two dimensions both receive the same index label, then they must have the same size. And that's basically just from an index shouldn't ever go past the length of another dimension. And then finally, the order of the output labels is going to specify the output's final permutation. And so that's going to let us do things like transposes really easily. Now let's use our rules to look at the example of summation along rows. Basically, we're just going through each row and adding up all the elements to get the output C. The first thing I'm going to do is label the dimensions of the input matrix A with the corresponding indices that travel along them. Since there's no other indices present, I'll call these first two I and K. The first rule says that we keep the indices that remain in the output. I know that I want to keep the index I since it indexes over the rows, so I'll put I in the output. Now we're already done, but using rule 2 we can see that the k-axis is being removed by summation. Finally, rules 3 and 4 are kind of trivially satisfied since there's only one input and only one output dimension, so the order and size don't really matter. Now, if this is a little tricky to think about, you can always go back to writing out the summation notation, or even writing a bit of code to make sense of things. For me personally, it's helpful to pay attention to where the indices are in the code as compared to the final Einsum notation. Now let's quickly do another example for practice, elementwise multiplication. If you want, pause the video. What do you think the Einsum notation should be? From a programmatic perspective, this is just a double for loop that goes through each I and j and assigns them to Cij. Mathematically, it can be written like this. Note that this doesn't even have a sum in it, it's just using the indexing notation. Now you can just extract these indices from the notation to get the final answer. And we can check that these make sense with our rules. All of the indices are kept, and all of the dimensions with the same label have the same size. Finally, let's look at an example where Einsum really shines. Let's say you're trying to compute this formula x transpose qx, say it's a cost function of some sort, and you know that q is going to be a 2 by 2 matrix and x is going to be 2 by 3. Now, normally you would need to take the transpose in order to get this formula, but with Einsum, you can actually just put x in normally, but then specify the dimensions along which you would like to multiply. Let me show you how this works. When I want to make this Einsum string, the first thing I need to do is give names to my first input. So since I have no other labels, I'm just going to call these I and j. Then I give labels to my Q matrix. I want to perform matrix multiplication along the axes of same length, so I'm going to call the first one I, and then the next one is unrelated, so I'll just call this K. Finally, I want to perform the last multiplication by aligning the K axes, and I'll call the last free dimension L. In the output, I know that I want the free dimensions, which are J and L, so I'm going to label them that way. Now this is nice, but let's say my boss comes over and tells me I need to make things more efficient by processing things in batches. With Einsum, this is really easy to fix. All I have to do is add a label for the batch dimension B, and then you can see where it shows up in my string. So now you've seen quite a few examples, and obviously this is just the basics, and there are a lot more advanced use cases, but hopefully you're equipped to use this function whenever you need it in the wild. Thank you. Go out and have fun with Einsum.